Okay, guys, good morning. So you just had the coffee break, so I hope you're all in a good mood. My name is Luis. I'm a data scientist at BNP Paribas, and I'll be presenting you the support vector machines. So I think you'll really like it. It's conceptually, it's a very fun topic. So just motivation. So why are we even bothering about this? Well, it turns out that support vector machines are actually very good out-of-the-box classifiers. Typically, when you're starting a problem and you're doing, well, mainly classification problems, and when you're starting a problem,
Sorry, let's just put this up there for a second. Okay, never mind. I don't know why that's not going away. Don't worry about it. Go ahead.
Okay, well, while they fix this, I'll keep talking.
He's literally just moving this down.
Yeah, so typically when you're starting a challenge in the classification problem, let's say, of any sort, and you have you don't really know where to start because you have a lot of estimators and this can be overwhelming. SVMs would be a good place to start. So this is why we're giving you this. And plus, conceptually, they're very cool algorithms. So let's get into it. Just,
Press this slide.
okay. Okay, so overview. So basically, we're going to start by looking at hyperplanes because they are the basis for all support vector machines. Then we're going to look at the maximal margin classifier, the support vector classifier, the support vector machine, and then some multi-class and regression extensions. So basically, we'll start from a very narrow scope, and then we'll enlarge from there. So 2 notes on this before I actually start. This is actually a lot of material, so it's quite impossible to completely cover this in 15 minutes, but I'll just skim some things over the top. So if at some point you're feeling like there's a lot of concepts being thrown at you and I'm just talking about things in a very high abstraction layer, then it's because it is true. And the second note is that usually, well, sometimes when people talk about the support vector classifier, support vector machine, and the maximal margin classifier, people tend to just say support vector machines for everything. They just use the same term for everything. Here we are distinguishing between them because it's important because conceptually they are different, and it's cool for you that are learning these models to see the differences and how you start from one and then you start generalizing from there. So first let's look at hyperplanes and what they are. Well, I mean, you should have a big idea of hyperplanes and what they are. So you know that if we have 2 classes, one obvious way to classify them, we just need to draw a line. And you say, okay, so all classes on one side of the hyperplane would all observations on one side of the hyperplane would belong to this class. All other observations belong to the other class. If you just have 2 input variables, then you can just draw a line. If you have 3, you can draw a plane, but you can extend this to any number of dimensions you want, right? A hyperplane exists in any number of dimensions. More than 3, it's hard for us to visualize, but they still exist. So that's basically the main idea. So if you want to separate in hyperplane, you classify an observation based on the sign of this equation here of the upper plane. So, but that's quite basic. So let's look at, so we have a separating hyperplane, we have a definition of how do we classify an observation based on which side of the hyperplane it is. Let's look at the most obvious classifier that we can build using this separating hyperplane, and the most obvious is the maximum margin classifier. And this, and what is it? So let me just define some terms before I go into the classifier itself. So the optimal separating hyperplane. So if you look at all your observations, the optimal separating hyperplane is the separating hyperplane that does the best job of separating all observations. And here we're talking about trained data, obviously. So when you're training your model, you want to find a separating hyperplane that does the best job, that maximizes the line, that maximizes the distance between all the observations in one class and the other. So margin, this is an important concept. If you draw a line, well, I'll show you a picture after, so this will be more clear. But if you draw a line, how close are the observations to the hyperplane, the separating hyperplane? So how much of a gap do you have between the closest observations and the separating hyperplane? And these observations that lie on the margin are called the support vectors. So that's where the name support vectors come from. These would be the observations that are closest to the separating hyperplane. And then, and then you'd classify the observation based on which side of the hyperplane that observation is. So this is a picture just to make things more clear. So let's say you have two classes over here. So identify by colors. So if you want to classify which class each of these observations belongs to, you could just draw a line. So this line here in dark in black would be your separating hyperplane, and this is the optimal separating hyperplane. So it's the separating hyperplane that maximizes the margin. These dashed lines would be our margins on one side and the other, and so the observations that lie on the margin are your support vectors. And you have here on the right the mathematical problem that we're trying to solve to find this hyperplane. Yes?
Do you always define margins on both sides?
Yes. Yes.
So margins can have a minimum distance that are different?
No.
No?
No. It's always the same, because it wouldn't make sense, because if one margin is bigger on the other side and smaller on the other side, you just move your separating hyperplane.
But then you can have one side of the margin without any points.
No. In which case would you have that?
For example, you define an hyperplane.
Yeah.
And the closest observation from the top side is here, and from the bottom side is here.
Yeah.
So the margin, what you are saying is margins are, this is the hyperplane, margin here, but here you have one observation, but down.
Then you just move your hyperplane lower, right? So if you have one observation here and one observation there, you draw your hyperplane in the middle, and then your margin is much bigger.
Okay.
You see, that's why it wouldn't make sense for one margin to be bigger than the other. It's always symmetric. So yeah, so this is the mathematical formulation. So basically, you're trying to find the coefficients, which we call beta, that maximize the margin over there. And here, the y, we are assuming, we define that the target variable is either 1 or -1, so it's either on one side or the other. And we're finding the beta coefficients that maximize our margin, which is m in this case. And then just a little constraint that beta has, all the sums of beta have to, beta squared have to be 1, because otherwise you could just set arbitrarily large beta, and that wouldn't make any sense. But yeah, so, I mean, this maximal margin classifier is very nice, but all of you were probably thinking like, okay, this is very nice, but in most cases it's completely useless, right? In most cases we can't just draw a separating hyperplane that separates the two classes, because we have noise and we have, well, real world data, and observations are mixed all over the place. So yeah, this is nice, and conceptually it's important to know, but it's not really useful in practice. And in fact, even if you could, for a particular problem, even if you could define an optimal separating hyperplane, there are good reasons why you shouldn't do that, because we're training our classifier on the trained data. And if you have an optimal separating hyperplane, you are necessarily perfectly classifying all of your training observations. So you have very high variance, because if one observation is enough to change the hyperplane, then your whole decision boundary changes. So you have very high variance, and I mean, you're most likely overfitting. So the question is, how can we solve this problem? Well, this is where the support classifier comes in. The support classifier, it's basically just an extension of the maximum margin classifier, but here we are allowing observations to be on the wrong side of the margin, and sometimes even on the wrong side of the hyperplane. That's why it's also called a soft margin classifier. You are allowing your classifier to make mistakes. When it's training, you are saying it's okay for some observations to be on the wrong side of the margin. It's okay for some observations to be on the wrong side of the hyperplane. So well, this leads to greater robustness to individual observations, because of what I just said. If you have some outliers that, in the case of the maximum margin classifier, would completely change your separating hyperplane, here maybe one is not enough to make a difference, or less. So this is a lot more robust. So when you apply your classifier to the test set, it will make a better classification for most of the testing observations. Of course, with support vector classifier, you can't guarantee that everything will be correctly classified, but I mean, that's classifiers in general, you can never guarantee that. So let's look at a picture to make more clear what I mean. So if you see here, the big difference between the other mathematical formulation, this one, is that now we are introducing what are called slack variables, and these slack variables are what allow your classifier to make mistakes. So and then I'll talk later in the next slide about this parameter C. This parameter C is the sum of all your slack variables, and it determines how forgiving you are of misclassifications. So this is an example of a support vector classifier. If you look here, we have observations on the wrong side of the margin, on the wrong side of the hyperplane, and that's okay because we are still correctly classifying most of the observations, and we are hopeful that this classifier will do much better on the test observations, which it's what we really care about in the end. So talking about this non-negative tuning parameter C, which is the sum of all your slack variables. This basically determines the severity of the violations that you are willing to allow. So if you have a very large C, then you are allowing for a lot of violations. You are saying that's okay. In the limit case where C equals to 0, you're back to the marginal maximal margin classifier. You're saying all observations have to be perfectly classified in training set. So you have here two examples, and you can see how this controls the bias variance, right? Because if you have C equals 0, then everything is perfectly classified, which means that a single observation can change your separating hyperplane, and by a lot, so you have a lot of variance. But then you have low bias, and then you have the opposite case where if you're allowing a lot of observations to be incorrectly classified, then you have lower variance because it's more robust to changes, but you have higher bias because it's not responsive to new data points. And you can see here, so this is an example. This is for the same data set as before. So for a small value of C, you're being very conservative. So you're saying, I want only a small number of violations. So you have a much smaller margin because that's a consequence of being more conservative. But when you have a larger C, then you're allowing more observations. You can see more observations on the wrong side, and this makes your margin a little bigger, makes your algorithm have less variance. So I mean, one obvious question that would be in your mind right now is, what's the optimal value for C? Well, it really depends on your problem. That's something that you as a data scientist has to figure out. That's about the C. So up until now, so we started with the maximum margin classifier, then we allowed for some misclassifications, but up until now, we're all still considering linear decision boundaries. And that's also quite a big constraint, right? In real life, a lot of things are not linearly separable. Even if you allow for misclassifications, or at least you wouldn't do a good job of classifying things using linear boundaries for most cases. So the next step is to use support vector machines. So this is an extension of the support vector classifier, and it's actually not such a trivial extension, but I'll just go over the basics here. So basically what this does is it uses kernels, and kernels are functions that basically enlarge your feature space so that you can use a linear decision boundary to the classifications. A kernel function is just defined as the quantifying the similarity of two observations. So let me try a bit more clear on what I mean by this. So if you get nothing else out of this slide, you can at least look at this picture, and what the kernel trick, it's called the kernel trick, what it basically is doing is that, okay, so we have all of these observations, and we can clearly tell by looking at this that no linear decision boundary will ever do a good job classifying this, right? Because it's non-linear. But if we use the kernel trick, we can project all of these observations into a space in which we can have a decision boundary. So if we project this into this, we can draw a line, and we do have a decision boundary. So in a nutshell, this is what the kernel trick is. Kernels are basically one way to do this projection, and they're a very efficient way. They do this using inner products. I won't go into the details, but it turns out that using kernels to do this, it's very efficient. So that's why this is a very good alternative to explicitly mapping all your input variables. And if you don't,
Just to see
yeah.
if I got it right. So you transform your data set into something else using the kernel tree so that you can use a linear.
Yeah, you project your data set, well, your observations into another space, a higher dimensional space, in which you can use a linear decision boundary. And this way you don't have, because there are alternative ways of, you don't need to use a kernel or a kernel tree to
You can make a circle.
Yeah. But even using a linear decision boundary, you can say like, okay, I want my coefficients to, instead of being beta 1 times x, beta 2 times x2, I can have beta 1 times x, beta 2 times x1 squared. So that way you're still using a linear function on a non-linear input space. But it turns out that using kernels is a lot more efficient and it does the job. So in fact, sometimes if you don't use kernels, it's not even like, it takes so much time that it's not even practical to use SVM. So that's why you use kernels.
How does the number of kernel functions relate to the number of features?
The number of kernel functions? What do you mean?
Is it just one kernel?
It's only one kernel function, right?
Ah,
Yeah.
okay.
And you apply it to all your observations.
You apply to every pair of observations?
Yes, because it's what measures the similarity between observations. Yeah.
Okay.
So yeah, but this is actually not a trivial concept at all. So again, if you are confused, then you can look at this picture and just keep this in your mind, this mental picture. Okay, I have this non-linear space. I will project it into a higher dimensional space, and I can use a linear decision boundary to separate them.
The transformation, is it, can you undo it?
Yeah.
In the original space?
Yeah, you can, but usually you wouldn't need to, right? You're just worried about which class you attribute. But I'll talk more about the transformations in the next slides. So what are these kernels, or what are these functions that I've been talking about? So one popular kernel is a polynomial kernel, and it can have degree, well, go wild with degree, you can go as far as you want. But this is a mathematical formulation, and this would be an example where a polynomial kernel would do a much better job than a linear kernel, right? So here, if you draw a linear decision boundary somewhere here, you would never do a good job. This is in the original input space, by the way. This is not in the projected input space. So any line you would draw here will do a pretty bad job of classifying these two classes. It turns out that using a polynomial kernel, you can do a pretty decent job of separating the two. So another kernel that's also very popular, it's the radial kernel. So it's in the original, in this case, in the original feature space, you can see it's kind of a radial decision boundary. That's where the name comes from. And this is the mathematical formulation. And if you look here, the kernel, so the similarity between functions, it decays exponentially with the distance between observations. So what this means is that it has very local behavior, right? Because if it's decaying exponentially, then observations that are very far away will basically not account for anything, because, well, it's decaying exponentially. So only the very close observations will make an impact. That's why it's called very local. And then the gamma is just some positive constant. These are all things that you need to then fine tune. All these things: C parameter, what kind of kernel you use, and then within that type of kernel, which kind of parameters you pass to that kernel. That's all part of fine-tuning your model.
The
Yeah.
dashed line, was that the margin?
Yeah. Yeah. So, okay, so up until here, I've only shown the examples of two classes.
Sorry. So are there is there like a part where the kernel function is learning as well? Are you learning a kernel function as well as trying to maximize margins? Do you do this, or is a kernel function more of a fixed thing?
Kernel function is more of a fixed thing. Yeah, I've never seen it done. Like, so maybe it exists. I'm not aware of learning the kernel function.
Always apply the exact same kernel function to everything. It's coded in. It's part of the model itself.
Yeah. Well, you choose your kernel function, and then you can choose it from a lot of kernel functions. But I mean, they're kind of well established.
Yes, there are kernels that are more computationally extensive, right?
Yes.
Some of them
Yes.
are really okay.
Yes. Yes. There are kernels vary a lot. So some of them are quite heavy computationally. Some of them are not. So, like for example, for the support vector classifier that I showed in the beginning, you have a kernel which is just a dot product between the observations. So that's very light. For the radial kernel, you have exponentials and you have sums of squares. So it's heavier. And there are some even heavier computational kernels, but yeah.
Probably one of the kernels, maybe the higher dimension.
Yeah. So yeah, but this is all things that you can explore on your own. Some of them are.
Just to clarify one thing.
Yeah.
So the kernel is just used to project data points.
Yeah.
And you are in your other higher dimensional space, and there you fit.
And then you fit your coefficients.
And you learn the betas. The betas are.
Yeah, the betas are your coefficients that determine the separating hyperplane. Then based on which side of the hyperplane your observation lies, that's the class that you attribute to the observation. So I mean, the kernels is just something you do to basically go back and use the support vector classifier. That's why it's an extension.
Sorry. And
Yeah.
these kind, if that's in this like regularization X for the regression, it's similar. So
It's
what
similar.
if
Yeah,
similar,
it's
right?
it's similar, especially in the way that it determines your bias variance trade-off, right? So yeah, you can draw some parallels. Yeah. So where was I? Yeah. So up until here, we've only looked at how support vector machines separate between two classes, and that's what comes naturally. But then the obvious question is, okay, so what if we have multi-class classification? Can we use a support vector machine just to separate multi-classes? Well, there is some work that is done around this, but the standard approach that is used is just to use the normal support vector machines and then use multi-class strategies. And these are implemented for you in sklearn, so you don't need to worry about the implementation, but it's still good to have an idea of how it happens, right? So it's not just, okay, so all the theory is about two classes and all of a sudden I'm using this for multi-class classification. So that's what this slide is about. So you can either use one versus one or one versus rest. So one versus one, as you might guess from the name, you're just comparing SVMs that do binary classification for each pair of classes, and then at the end you just assign the observation to each class it was most frequently assigned. Or you can do one versus the rest, which is you fit all k SVMs. K is your number of classes, by the way, and then you assign the observation to the class for which your distance to the maximal margin to which you assign your observation to the class which maximizes the distance to your hyperplane. Regression. So usually when you use support vector machines, you use them for classification. At least, well, in practice this is an empirical observation, but in practice I've seen them mostly used for classification. But nevertheless, here we have just just for you to know that they can also, there's also like an extension to regression, and it's basically the same concept. The only difference is that now you have your separating hyperplane and use that to make your predictions. So you still find your decision boundary. Well, you still find your line using the concept of margin and support factors, and then when you have the new test observation based on the variables that you observe, you find the point in that line that corresponds to your observations, and that's your that's the value that you predict. So it's a continuous value. So that's the extension to regression. This is not so used in practice, but I think it's still good for you to know. So recap. This is a lot of stuff, and like I said, like a lot of things were just given, like why do kernels use in their products, and that magically works. Well, that's for me to explain that it would take a very long time. But just to recap, so we started at looking at hyperplanes in p dimensions and how they can use to separate classes. Then we looked at the maximum margin classifier. So here we're only looking at the subset of problems where you can draw a hyperplane that perfectly separates all classes. We went a step further. So how can we use the support vector classifier with a soft margin to allow for some misclassifications? We went another step further. How can we use SVMs with kernels to accommodate non-linear decision boundaries? And then we discussed the multi-class and regression extensions, just to see how can we apply this to multi-class and how can we apply this to regression. So, well, okay. So, and I also have here some links if you really enjoy this topic and you want to go further. I've left you some pointers. Yeah.
When you use the kernel function on your data, do you lose the interpretability of the data?
You would, yes. So it's the same problem that happens when you use a PCA, right? You lose the semantics of your original observations. But here, it's not as relevant because the projection is deterministic, so it's always the same. So even if you don't know what that intermediate step is, in the end, you're really only concerned about which class each observation is assigned to. So you can look at which class the observations were assigned to, and then you can go back and look at the original feature space and take the semantics from there. So okay. Usually that's not a big issue. What is an issue is trying to figure out which kernel is the most appropriate given the original input space. I mean, I gave you some obvious cases, but in real life, sometimes it's not that obvious. Sometimes you look at your input space, and sometimes you can't even look at it because it's like 200 dimensions. You're measuring 200 variables. So the problem there is which kernel do I use? You know, well, you don't know. So that's part of data science job is, okay, what kernel do I use? What value sheet do I use? What parameters do I use for this specific kernel? You know, that's part of the job. Yeah. So, questions? Maybe?